Okay, so today we're going to continue on with the unit circle. Going to go back and answer a question about a problem in the book when we get started here. But today we're going to be using the unit circle, and I'm going to kind of drill you a little bit and see how good you are with it for coming up with these different trig ratio values for our 16 familiar angles. And then we want to wrap up the discussion on trig properties. So we'll practice with the unit circle. We'll look at some of those trig properties, and then we're ready to start the introduction to taking this angle measure and see what the pattern is that actually creates a function for us. And actually there's 6 different trig functions associated with each of the 6 trig ratios. So we'll start developing that today, and then next week we're going to spend the whole week on dealing with all 3 class sessions. We're going to deal with graphing the different trig functions, and we're going to be stretching and squeezing them and flipping them upside down and start to see some real practical use for that stuff. Okay? So first of all, there's a question asked just a few minutes ago about question 123. Happens to be on page 380 of our book, so I'll quickly put that up on the screen here. Page 380. Number 123? Yes, thank you. As a matter of fact, I had made a note in my book to talk about that problem, so I'm glad you brought it to my attention. And I can zoom in on this so it'll show up on the recording. Okay. So, this is a fairly practical kind of problem, and what you'll observe is you got 2 beach houses separated by a river, and then there is sand on the beach, and then there's a paved road. And what we want to do, let's see, there's some distances given here. Each of the houses on the beach are 4 miles from the river to either side. And what else do we have going? Oh, Sally can jog 8 miles an hour along the paved road. That's a fairly good jogging pace. And then it's only 3 miles an hour, though, which is kind of a decent walking pace on the sand. And then I'm just continuing to read through this. And they actually, I'm going to work on developing the equation, which then goes onto the up onto the other onto another page here in the book. But I'm going to actually work on developing that equation with you folks right now, and then we'll answer the various parts of the question. So what we're trying to develop is the time it takes for her to jog from one house to get to the other house. So she's got to run on the sand a certain distance, and then she gets to run on the pavement at a faster rate, and then goes back onto the sand, and the path she's going to take is going to be a regular trapezoid sort of shape here, right? So we're just doing a symmetric type of geometry problem here. And you can see that this angle that she jogs at from the house to get to the road could vary. She could jog, if she wants to do the shortest amount, pretty obviously here, if she wants to do the shortest amount of running on the sand, she'd run straight out from the beach, from the house, straight to the road, and then she'd spend a longer distance here on the road and then straight back into the house. So what we want to do is develop an equation for the amount of time it takes for her to do the entire trip. And one other comment here, the houses are 1 mile from the road. That's a lot of sand. Okay. So it's kind of an idealized problem, but nevertheless very interesting. So this is going to be running on the sand, and then now she's going to be on the road, and then she's going to go back on the sand, and this is going to be sitting at some angle theta, and this happens to be 1 mile. And these houses are separated along the beach a distance of 8 miles. Okay, so our objective, so here's a generalized drawing our objective is to develop an equation, a function, for the amount of time as a function of angle theta. And that should make sense to you, depending on that angle that she runs at on the sand. This is sand. Should make sense to you that it's going to take her a certain amount of time to run this, and then she'll run this at a different rate, and then back on the sand again to finish the trip. Make sense? Okay. So, let's use what we've learned. We know this total distance between the two houses along the shoreline is 8 miles, and so then there's a portion of this down here that is paved on the road. Now, here's an adjacent side. Why don't I just label, let's go over here and look at this little right triangle. Let's call this little segment right here X. X. Now, what we observe is that there is a trig ratio here that says that the tangent of angle theta is equal to, here's a right triangle, opposite side over adjacent side, so 1 over x. Everybody comfortable with that? Should be. Okay, so distance x, right here, the ratio of 1 mile divided by x is equal to the tangent of this angle. Right? Now, if I multiply both sides of this simple equation by x, then that will move x effectively up onto the left side over here, and reduces out on the right and leaves a 1. And so we have x times the tangent of theta, and then we divide both sides by the tangent of theta. It's a beginning algebra level type of process here. And so we then end up with a description of x being 1 over tangent of the theta angle. Okay. Now, how much time is she, well, let's see, what's this distance on the road then? If I have an expression for x, then what's the distance that she'll be running on the road? Okay, we have a total distance here of 8. It would be 8 minus 2x, right? Looking at the picture, 8 minus 2x. And then by replacing x with our 1 over tan theta, we then have an expression for this distance. So the distance on the road, and what I'm going to do, this is, actually, let me go back here on my notes. This is what we're looking for right here. So we have a description of the problem in a drawing showing the given information, and then we write down what we're looking for. So it's an abbreviation of the whole problem. Then we're starting with a little simple calculation here and get this piece. Then on the road, let's take a look at that. The distance is equal to 8 minus 2x, okay? So the length on the road that she has to travel, I'll call that L sub r, is going to be equal to 8 minus 2x. So the length on the road that she has to run is going to be 8 minus 2 over tangent of theta, when we put the 1 over tan theta in right here. That's the distance she has to travel. Now, we know that when she's on the road, she can run how fast? They told us in the book. 8 miles an hour. Pretty good jogging pace. And so she can jog on the road at 8 miles per hour. We know distance equals rate times time. So let's go back to something really basic here. Distance equals rate times time. And we know that if we wanted to find out the time she's spending on the road, we would take the distance that she's on the road and divide that by the speed that she's running. So it looks like we would be able to, while we're still on the road now, we're still on the road, the distance she's covered is 8 minus 2 over tangent of theta, that's the distance, divided by the 8 miles per hour that she can jog. So that's the amount of time she will take while she's running on the road. Can you folks do something like that? I mean, develop something like this? I mean, all you have to do is start with the little pieces of the puzzle and then start thinking your way back to basic fundamentals and then develop these relationships. So here's the amount of time she's on the road. So this is the time, I'll put a little R underneath there indicating road, time on the road. Now, we can clean this up a little bit, can't we?
Yes.
This is a common denominator. And so that means then that's the denominator associated with each of these fractions as well up here. And so what we could do then is simplify that and write it as 1 minus 1 over 4 tangent of theta. For the time on the road. Okay, so that's one piece of our puzzle. Next, we have to talk about running on the sand. Running on the sand. Can you guys with the camera maybe try the other camera and zoom in a little closer so you can get the glare off the screen there a bit? Might be helpful. Okay, when we're on the sand, it looks to me like we need to figure out what? Yeah, we need that distance. So we have to do a calculation on the sand similar to what we did on the road. So the time spent then on the sand is going to be the same sort of calculation. Distance on the sand divided by the speed running on the sand. So the distance on the sand is a Pythagorean relationship here in this right triangle. So the distance on the sand squared is going to be equal to 1 squared plus x squared. So the distance on the sand is going to be the square root of 1 plus x squared is going to be 1 divided by tangent squared of theta. And we talked a little bit about squaring trig functions yesterday near the end of the last session. Right? Where we came up with a Pythagorean identity, sine squared plus cosine squared equals 1. So it's kind of similar here. Is everybody okay with this so far? Now, we're playing around inside a radical, aren't we? We're inside a radical. So we have to tidy that up a little bit. Let's tidy that up. It looks to me like a common denominator in there would require a tangent squared inside there, doesn't it? So we're going to have a radical of tangent squared theta plus 1 over tangent squared theta. And that's one big radical. But you feeling? Got it? Okay. Next step, what do you think we want to do? Try to clean that up a little bit more before we take that distance, that's a distance on the sand, and divide it by the speed she runs on the sand. So I want to tidy that up a little bit. Now let's go back up and look at something that we saw in the last session. Remember this? Sine squared theta plus cosine squared theta equals 1. Pythagorean identity. Think of your unit circle. You have your x reading is the cosine of the angle, the y reading is the sine of the angle, the sum of the squares of those is equal to the hypotenuse squared on your unit circle is a 1. So we have that. Now, if I want to see what happens to build a tangent out of this, if I divide both sides of this by cosine squared, like we did in the last session, every term divided by cosine squared, look at what we get here. Don't we see tangent right here being squared? Mm-hmm. So we get tangent squared of theta plus 1 is equal to 1 over cosine squared of theta. So back down here in this radical, you observe tangent squared theta plus 1 could be replaced with 1 over cosine squared right down in there. So let me go this way with that equal sign. And so I have that radical for the distance on the sand is going to be 1 over cosine squared of theta times 1 over that denominator that was there, tangent squared theta. Here's another little thing I learned years ago. Sometimes you have an expression with a radical and you have some other stuff even following it. And so I always put a little tail on my radical symbol, little tail on the radical symbol here to indicate that I'm at the end of that. It's just a habit. Now, does this clean up?
Are you adding those together?
No, hold it. Is there, look at, isn't this numerator right here 1 over cosine squared times, yeah, secant squared, 1 over cosine squared or secant squared, right? So that's 1 over cosine squared. That's multiplied times 1 over tangent squared, not added. There's no plus sign here.
So like, because you have vertex curves, right?
What if you had something, well, it's fractions, okay? This is 1 over cosine squared, and this is still 1 over tangent squared.
Yeah.
Got it?
Yeah, I don't
Okay.
know what I was thinking, yeah.
Other people okay with this on the fraction work? Okay, and then this is kind of messy and it's fairly involved, and it's more involved than actually what the problem is in the book. I'm actually developing the formula they gave you in the book for that problem. Okay, so this is actually pretty good practice, even though it's not addressing the practicing with the unit circle. So let's go ahead then and come in here, and this tangent squared, we could replace that with what? Sine squared over cosine squared. So I could come in there and replace that denominator with sine squared theta over cosine squared theta, and then these cosine squared thetas disappear. So this whole mess degenerates to, I better go to the other board, the distance on the sand degenerates to the radical of 1 over sine squared theta, which reduces to, when you take the square root of the numerator, you get 1. When you take the square root of the sine squared, you get sine theta. So the distance running on the sand is equal to 1 over sine theta. Now, look at all that work we just did. Let's come back here to this board. Look at all that work we just did. Come back up here for just a second and look at this. Angle theta, here is your distance on the sand right here. Look at what the sine of theta is by definition. Isn't the sine of theta opposite over hypotenuse? So if you multiply both sides by d sub s, it kicks it up over here. And if you divide both sides by sine theta, it drops the sine theta down under here.
Oh, Robert.
It's kind of like jogging in the sand, isn't it? Doing this, right?
Yeah.
And this is a much quicker, cleaner way to get at what that distance on the sand was. Right? I wanted to go through practicing algebra and fractions and radicals with you a little bit. That's the reason I took that path. Okay. And jogging in the sand is actually really good for you. And doing this kind of thing is good for you as well. Okay.
Unless you're bad news.
Now, at this point, we forgot what we're supposed to be doing. We're really supposed to be finding what here? The time it took running on the sand. So the time running on the sand on one side of getting to one of the houses is going to be the distance on the sand divided by the rate running. So now we have 1 over sine of theta divided by the rate, I think it was 3 miles per hour, and that reduces to 1 over 3 sine theta. And that's the time she spends getting from the road to one of the houses. And from our trapezoidal description earlier, we have 2 of these legs, don't we? Mm-hmm. Okay. So what we're going to have then, the time as a function of theta is going to be made up of the time running on the road plus the time running on the sand, and it's actually going to be twice the time running on the sand from that value. Notice over the years I've gotten into a habit, which we're trying to teach in most of our courses, is we want you to write step-by-step development and show your work in a way that makes sense. And one thing you might do is insert the English comments that I've been encouraging you to do. The time running from one house to the other is then going to be this, time on the road plus 2 times running on the sand. Then we drop in the given information, and we should come up with an equation that was shown to us in the book. And so we have the time on the road is 1 minus 1 over 4 tangent theta. And then we have to add to that 2 times this value. And does that agree with what's in the book? Right there. I think that agrees, doesn't it? And I can zoom in on that. If you're watching the DVD, you might not be able to see it that small. There it is right there. And you might be able to get it, if you guys in the control room push a button, you might be able to do something back there in the control room to get this to, give us better resolution on that. Maybe, maybe not. Okay. Now, what are the various questions that were asked? Because we didn't really even get to your question here. And this is, even though I'm not playing with the unit circle, this is really good practice. It's you're seeing something kind of practical on how you can develop something here. So that's the reason I'm willing to spend the time on it. Marty, what are the questions then that are asked?
Calculate the time t for theta equals 30 degrees.
Okay, so at 30 degrees, we're just going to put this in there, right? Okay. So we want part A, we want to figure out the time, the amount of time if you use 30 degrees in the equation.
Also, the question goes on saying, how long is Sally on the paved road?
Okay, and then that's part B?
No, it's still in part A.
Okay, good, okay. So here's at 30 degrees. Now, do we need a calculator if we're on 30 degrees?
No.
Good, I'm glad you said no. Because we've spent a lot of time trying to understand clearly what's going on for these various 16 angles we've talked about. And 30 degrees is one of our primary ones, right?
Yeah.
So we know our trig ratios, don't we? Yes, we do. Okay. So at 30 degrees, we can just drop in here without a calculator. Now, here's something you'll find useful. What I'm doing is I'm going into this equation right here, and I'm dropping in 30 degrees. Now, when I do that, this is going to be the tangent of 30 degrees. Little simple thing for you to remember. We talked about tangent at 45 degrees, we know is 1. And we know that when we're below 45 degrees, we have a tangent value that's smaller than 1. It's easy at 30 degrees for you to remember it. At 30 degrees, here's your tangent of 45 there, is at 30 degrees, the tangent of 30 degrees is 1 over the square root of 3. That is smaller than 1, isn't it, that value? Okay, that's not too hard to remember. What do you think it's going to be at 60 degrees, folks?
Double that.
A little more than 1.
What it is the square root of 3.
Oh,
Square root of 3. So, why not learn it? Because these angles show up all the time in textbooks and on quizzes and tests. So if you know those, you'll already know pretty much kind of the exact values instead of having to go through a calculation of the sine divided by the cosine to come up with those. Okay, fairly simple. Bigger than 1, less than 1. Okay, so in here then, I'm going to put in at tangent of 30 degrees, 1 over the radical of 3 down there in that denominator. And then I'm adding to it finally 2 over 3 times the sine of 30 degrees. We all know that. 1 half. Okay. So we can clean that up. I'm not going to take the time on the algebra or the arithmetic actually to clean that up with you right now, but that's how you'd answer that question. The other thing you ask as part A in the book is it said what distance does she run on the road, right?
yeah.
And we have an equation for the distance on the road over on the other board. The distance on the road, I'll just write it down here again, is 8 minus 2 over tangent of theta. So at 30 degrees then, this is also a function of theta. So all you have to do is use 30 degrees there and put a 1 over square root of 3 in there. What are the other questions asked in that problem?
Well, the other questions, B and C, are just calculating the time for theta equals 45 and theta equals 60.
Okay.
And the same thing, how long
Yeah.
is Sally on the paved
Yeah.
road? But
Okay.
then question D
Yes.
is the one that gets interesting, because it says to calculate the time t for theta equals 90 degrees, describe the path taken. Why can't the formula for t be used?
Okay. So let's look at this briefly at 90 degrees. If you use this formula and put 90 degrees in here, you're going to be talking about, I'm going to show you actually how you can use this formula, but if you try it on your calculator, it'll blow up on you. Okay? Well, your calculator won't blow up. It just won't work. Okay. Now, at 90 degrees, think about what we did with tangent. Think of slope, right, of your standard angle. So when you get up there near 90 degrees, that slope is getting bigger and bigger and bigger, and when you're at 90, it's undefined. Blows up to infinity. So mathematically, this value is approaching infinity, is it not?
Yeah.
And what happens when you divide by infinity?
It's undefined.
When you divide by infinity, what's 1 over infinity?
A very small number.
Doesn't that head towards 0 in the limit?
Oh, yeah.
Yeah.
Isn't that nice?
So you're dividing by
Don't have to touch your calculator. Does that make sense to you? 1 over 1,000, 1 over 1,000,000? Think about it. 1 over 10 million? Heading towards 0, isn't it? So that term disappears, and what we're left with here is 1 plus 2 over, what's the sine of 90 degrees? Think unit circle.
One.
It's the y reading off our unit circle, isn't it?
It's 1.
It goes up to 1.
Yeah.
So that becomes 2/3. So you get 1 2/3 miles. Oh, excuse me, 1 2/3 hours,
approximately, right?
approximately. Yeah. So you get 1 2/3 hours of running time, which is a pretty good amount of exercise. Part on sand, part on the road. Okay. I diverged from practicing with the unit circle considerably here.
So why does it say that it can't be used if you just used it?
You cannot pop this into your calculator
Well,
and
if
run
you use
that.
a calculator, but if you just
Maybe the
do it.
question was.
Well, you can do it this way, like I
Right.
just showed you. Yeah,
Yeah.
works fine.
Okay.
Okay. Yes,
How would you figure out the shortest amount of time to run?
that was the question. How can you figure out the shortest amount of time? Makes sense. That's an optimization problem, isn't it? And that's very useful to know. You go, oh, I'm really hungry. I want to get from, there's no food in this beach house. I want to get to that other beach house as quick as I can. What path do I take?
Straight line.
Well, you can't do a straight line because you got a river. Okay. So you got to get out to the road, you got to go down across the bridge, and you got to get back to the other house. Right? So it's an optimization problem. So what's going to happen when you take this function, and you did this back in college algebra. You take this function in your calculator, and I'm not going to take the time right now, but we will be doing things like this real soon. Time is a function of theta, and draw the graph using, and I'd probably be in degree mode. And when I'm at 90 degrees on the angle I take from the beach house, I'm going to be getting a value of 1 2/3, which is 5/3 right here. At 90 degrees, it should be giving me a value of 5/3, which means 5/3 hours. And then if angle theta is 0, we can't do 0, can we? No, because here's the house, here's the other house, here's the road. If we did theta equals 0, we can't do theta equals, there's a minimum angle of theta, isn't there? Because there's a bridge here and a river. There's a minimum angle theta here based on the geometry. 1 mile, 4 miles. See the tangent there? So that's the minimum angle, and that's going to be down in here somewhere, the minimum angle that you could possibly use to be able to go from house to house. Yes?
Well, at the rate you run, was it 3 miles an hour in the sand, so
You'd be on the sand the whole time.
even though you can find the minimum angle for theta, you still, it could be taking you longer because you're running farther in the sand at a slower rate.
Oh, totally. Matter of fact, what's going to happen is there's going to be a certain amount of time here. It's going to be significantly greater than this probably at this theta minimum allowed. And then what's going to happen is this is going to come down and probably do something like this somehow. And I'm not sure what. But somewhere in here is going to be the minimal amount of time for at a particular angle. Okay, let's end this segment, even though I was not talking about using the unit circle. We'll come back to that here in a couple minutes. So we'll move on to the next segment. And I want to start developing trig functions with you and also touch on the properties. Okay? So you guys can end this segment and we'll roll to the next.